I would like to request a change in the schedule. Noah's not here for much the same reason. My grandmother died on Friday morning, and the funeral is actually going to be on the 23rd, and so I'm going to be gone that day. And so what I would like to do is to take advantage of the time that is set aside for group project day. That is lab tomorrow. There is no lab. It's set aside so you don't have to work on the group project tomorrow, but so you have time allocated for the group project whenever you decide to do it. I would like to request that we come at lab time tomorrow and I'll lecture for an hour. And then on the 23rd, we will not have class that morning. That way we don't fall behind in the lecture schedule and, I can go look down on the funeral. So are there any objections?
So that means we have open, whatever that called, the reading course tomorrow.
There will not be a reading course due tomorrow, no. The one that's due on Wednesday will have questions that would be appropriate for tomorrow, but I'm not going to say, oh, you've got to find time to do that extra.
Okay.
Any objections? Right, I don't want to just tell you have to, since it's in the schedule. Okay, so we will be here tomorrow for lab time for a 1-hour lecture. Okay, we're going to talk some more about magnetic application things. We ended on Friday with amperes law. And Ampere's law is the way that we calculate the magnetic field due to current. And so we talked about the right-hand rule and how we determine the direction. You've had some good experience with that in the homework. There is another very quick and simple example of Ampere's law that is necessary. It gives you a necessary equation that probably everybody just looked in the book. But I want you to see where it comes from. And that is the equation for the magnetic field produced by having current go through a wire. So I have current going through a wire, creates a magnetic field. How big is that magnetic field is the question. So that's a classic application of Ampere's law. We're going to go through a few applications of Ampere's law today, and this is the first one. So if you have a current carrying wire, i.e. this, the first thing is, we already talked about the right-hand rule and the symmetry demanding that you have to have your magnetic field lines doing circles. Just spread out where the mess is. I'll spread it out even better. And so if I'm going to use Ampere's law said that I choose a surface of my own design, or actually a loop of my own design. It doesn't have to be a circular loop. It can be any shape of loop, but I want that loop to be one where I can calculate the, quote, circulation. And that circulation was, that's the calculus form. Integral of B dot dl. What does a dot product mean? Multiply parallel parts. So we're multiplying the parallel parts between what's B with the vector sign mean? Magnetic field. And the dl with the vector sign means each little piece of length. So the non-calculus form, we still have the dot product because we're still multiplying just the parallel parts, but we put a summation instead of the integral sign because they mean fundamentally the same thing. And then we just have the L for each piece of length. So we want to calculate that B dot L along the length. Going back to our picture here, though, we have a certain symmetry. We know that the magnetic field has to be doing set circles around the wire. And the magnetic field strength can't vary if I stay at the same radius, because what difference does it make what angle I view if it's a wire? It only matters how close or how far I am. So the magnetic field has to be constant if I'm at constant radius. So to do this calculation, I take those symmetry ideas and I say, because of this cylindrical symmetry, I'm going to choose, that was too blue. So I choose a circular loop around the wire for Ampere's law. Now here's a really important question. Is there a piece of wire that's going in that loop? It's a really important question, so I'm going to wait for an answer. Is there, see, it has that circle that's drawn that has a whole bunch of little, supposed to be compasses on it. I'm going to use that for my calculation. Is there a wire there that I'm calculating along? No. Is there anything there I'm calculating along? No. It is just a path for calculational purposes. That's real important because sometimes you start trying to think, now what's there? There's not something there for the calculation. It's just where we're making the calculation. So I choose that circular loop, and because of our symmetry, as I go along that wire at all points, the magnetic field is parallel to the length. Well, that makes life easy because if they're parallel, a dot product is multiplying the parallel parts. So B dot L just becomes B times L. That's easier. And so if I go all the way around the loop, if I add up all the pieces, I'm just going to have B times the circumference. So in my application here, this just becomes B times the circumference. What's the equation for circumference of a circle? 2 pi r. So B times 2 pi r is equal to, and then the other side is mu 0. What's mu 0 or mu naught or mu watt? First, since the student asked, mu is the Greek letter M. And it's the permeability of free space. That's something that tells you about how magnetizable a vacuum is. And you might point out, and rightly so, isn't this going to be in air, not in vacuum? And the answer is yes. Yes, it will be in air, not in vacuum, almost certainly. But the difference between vacuum and air is very small, so we just stay with it. And then times the current that is going through my loop. So if I treat this loop like it's a piece of rubber that's stretched along the loop, I say how much current is going through that rubber. So I have one wire going through that piece of rubber in my mind. And so the current is just going to be the current going through that one wire. I've got to be careful. Fortunately, I'm far enough away from my car that I don't think it's going beep, beep, beep. I stay with my hand in my pocket, I accidentally press the alarm button on my key fob. It's the only time it ever gets pressed by accident. So the I enclosed is just the current in that wire. Now I simply take this equation and solve it for magnetic field. So if I solve this for magnetic field, I'm going to have to divide both sides by 2 pi r. And that gives me the magnetic field is mu naught times I in the wire over 2 pi r, where r is the distance from the wire. So Ampere's law gives me a direct, simple equation for what the magnetic field is at some distance r away from a wire produced by current going through the wire. So that's the simplest application of Ampere's law. And you use that over and over on the homework assignment that's due tonight, right? And like I said, I assume you just looked at the equation. It's a simple equation. But I want you to see where it comes from. Now, what about that permeability of free space? Its value is, if I remember right, four pi times 10 to the minus 7, and it's going to have units of, oh boy. Honestly, I don't remember its units. I'm sure I could figure it out, but I don't want to. Tesla times meter over ampere. How's that? I just got that from looking at Ampere's law. Pretty sure that's its value. Where does it come from? We'll get to that. If somebody wants to look up the value real quick to correct me, if I have the 4 pi wrong or something, I don't want to be wrong. Did you look it up already? I just want to be checked rather than to tomorrow realize, oh, I did that wrong. Okay, so our first clicker question of the day. A wire is carrying current to the right on the screens. That is, we have a wire carrying current like this. Is the magnetic field produced by the current at a point directly below the wire? So here's a point directly below the wire. Is it going up, going down, going to the left, to the right, into the screen, or out of the screen? So just to make sure we're clear, this will be up, this will be down, this will be right, this will be left, and of course, into the screen, out of the screen. Hopefully we're pretty clear. Question? Did I not start the session? Okay, I'm going to make everybody answer again. Yes, I did not. Crud. Sorry about that. Well, everybody remember your answer. It's that kind of... Polling in session. I am so sorry. Okay, answer now. So, Abigail, Ashley. Okay, everybody's answered. Okay. There's what I believe the answers were. It didn't. It showed me until I, moved forward. So let's go straight to Lauren for an answer.
I said I was going into the screen because if you use the right hand rule in the direction of the current, your hand's going to curve clockwise, and at that point down at the bottom, it will be going into the screen.
Okay. Put your thumb in the direction that shows the current. Wrap your fingers around the side that's below. In this case, my fingers are going into the screen. And so that was the correct answer, into the screen. So while it was not a majority answer, it did have the plurality, and you were right. Good answer. I'm always very careful to point out that, 9 out of 19 is not a majority, just in case anybody gets confused on what constitutes a majority. How many would you have to have a majority? What'd you say? Well, if it was 100 people, sure. But since it's 19 today, it would be 10 to be a majority. So if majority ruled, we'd have no rule. Okay, now, magnetic field due to a current that's a little bit different. Here we have a current that's going in a loop. And so if we use the right-hand rule on that loop, and of course, let me just take, this is my world of simple demonstrations. Here's a loop. And so if I have the current going in this loop like this, I'm going to first take a hand. Which hand should I use? The right one. And I'm going to point my thumb in the direction the current is going. So the current's going like this. And on the inside, what direction are my fingers pointing? They're pointing toward me, away from you. As I go around, what's happening is direction my fingers are pointing on the inside. Staying the same. So every part of this loop is making a magnetic field, and the center is going this direction. Since every part is making a magnetic field that's in the same direction inside the loop, that's going to make the strength of the magnetic field inside the loop pretty strong, because every piece of the wire is adding together. Now on the outside, it's going toward you, right? And as I go around, of course, my fingers are going to stay pointing toward you everywhere I go. But the outside here is the same direction as it was inside here as far as, well, same direction. It's the same side of the wire. And so the magnetic field created by the current here is the opposite direction of the magnetic field created by the current here if I'm looking outside of the loop. So outside of the loop, we're going to have some destructive addition. So what happens is the magnetic field inside is concentrated. The magnetic field outside is much weaker. So when we talk about the magnetic field created by current in a loop, we focus on the magnetic field that's inside. We can't forget the magnetic field outside, but we focus on the inside because that's where it's much stronger. Now, if you look at the magnetic field lines, such as are drawn in our diagrams, we have magnetic field lines that look like this here, I don't know what color to call that, maize. Inside, the lines are very close. What does it mean if the field lines are very close? Strong. Outside, they're farther away. That means it's weaker. So you have the stronger magnetic field inside, the weaker magnetic field outside. And just as we learned is a rule, the lines all close on each other. So you have to have the same number of magnetic field lines outside as you have inside. The difference is the ones outside are much more spread out, much weaker field spread out over a much larger area. Inside, it's a much stronger field in a smaller area. This direction came from applying the right-hand rule at each point along the loop. Now for a simple right-hand rule, another one for us. If I have a loop with current in it, I can find the direction of the magnetic field. Instead of going along each point like I talked about, I can just take my hand and wrap my fingers to the direction the current is going in the loop. So in this case here, I have the current coming up on your left, going down on your right. And so I just take my right hand and wrap my fingers in that direction. And my thumb is pointing away from you toward me. That's the direction of the magnetic field inside the loop. It perfectly agrees with what I got when I went like this all the way around. So that right hand rule, wrap your fingers of your right hand the direction the current is traveling in the loop, and then your thumb points the direction of the induced magnetic field in the center of the loop. So one of your homework problems today is about a compass. And it asks you, which direction is it going to tip? Well, if you have a magnet in a magnetic field, there's a torque to make what happen? What should happen if you have a magnet in a magnetic field? It'll align. You have a torque to make the magnet align with the magnetic field, so magnetic field lines come out of the north of the magnet and go into the south. And so in that case, you had a loop that was like this, and it was making a magnetic field that was up. And so if there's a torque to make it align, it should tip so that the top shifts to pointing north to be aligned with the Earth's magnetic field. Now, what's the strength of the magnetic field inside of that loop? Well, it's not exactly the same as what it was for a wire, but it looks very similar. It's mu watt, that permeability free space, times N. N is the number of loops. Often instead of loops, we'll use the word turns. So the number of turns, the number of loops in my coil times the current that is going through the wire divided by 2R, where R is the radius of the loop. Now, if we compare this equation to the one I found above, what was the R here? R, this was for a single wire. There was no radius per se, except for my imaginary circle. And that R was the, were you answering this or another question? Okay, so the R was the distance from the wire here. So when you look at these equations, it's important to understand what the equation has as its variables. R does not mean the same thing in every equation. You have to know what it means in these equations. So you'll have all the equations given to you, but you have to know what they mean and how to apply them. Okay, what was your question, Ashley?
Oh, I was just wondering if the permeability of free space, if that was different for different things, kind of like how for our last test there was whether it's like grow or something and it differed with material,
Yes.
and I wasn't for sure if the permeability of free space would also differ with different things.
The permeability of free space is more directly compared to the permeability, the epsilon. And remember when we learned about capacitors, we learned that we could put in different materials with a different dielectric constant. And so we used in those materials that epsilon equaled kappa epsilon 0, where epsilon 0 was the permittivity of free space. We have the same type of thing with magnetism. With magnetism, we have the permeability of free space, and we'll have mu is equal to, and I don't remember what we use for the symbol out here, mu 0, and there's a constant here.
But that number never changes. Right?
Well, the mu 0 never changes, but if you go to a different material, the mu does. So mu in iron is like 1,000 times higher than mu in air. And so mu 0 means in free space. If you put something in this coil that's not air, and not vacuum, since technically mu 0 is talking about vacuum, then you have to account for that as what you're thinking. Okay, now for solenoids. Yes, ma'am.
So if the mu is different, would it be specified then in the question?
It would generally say something at least like you have iron in there, then you have to look up mu for iron. But yeah, you have to have something to indicate what mu is, and it could be telling you what the material is, and you look it up, or it could tell you what the value is.
Okay.
Okay, a solenoid. A solenoid is a bunch of loops, and you should be saying, well, what's the difference in the coil we just looked at and a solenoid then? And the difference is a solenoid has a length factor to it. What we did there was assuming that all the loops were exactly the same place. The equation for the magnetic field from a coil here was assuming that they're all at the same place. So circular current loop, that works perfectly if it's one loop because there's no spread. A solenoid has some spread there. And so here's an example of a solenoid. Give you a good medical example. Back when I was in college, I was playing football, flag football, because, you know, I went to Loma University, playing on the varsity flag football team, tore my shoulder. So I had to have surgery on my shoulder, and after 2 years, I still couldn't throw a baseball. And so I went to Dr. Benjamin Lau, and he was working on me, and he decided to use a solenoid as part of my medical treatment. He put this big solenoid over my shoulder here, and then he plugs it into a little device. And, you know, as a physics major, I'm like, what in the world? This shouldn't do anything. But within like a month of starting that therapy, I was actually able to start using my shoulder again, which made me very happy. So I believe that it did something. Now, what is a solenoid fundamentally doing? You put current in those wires, and what's it going to create? A magnetic field. And so he was basically putting me in a magnetic field, but it's not just a static magnetic field. I mean, when I'm standing here on Earth, I'm in a static magnetic field. And if I spin around, I guess I'm in an oscillating magnetic field, in my body's frame of view, but not a very strong one. So what we had was a machine that was putting an oscillating current. I don't know what the frequency was, but the frequency is supposed to be tuned to the body's natural frequencies of electrical communication to try to stimulate the tissues to have transport of nutrients. That was the idea. And so this is one equivalent, really, of the TENS machine that puts electric fields across tissue and tries to match the frequency to simulate the natural frequencies and get the body to bring more nutrients. So I believe it worked for me. Once again, though, this is anecdotal evidence at best. It's not conclusive. You know, if you want to know if it really works, you have to have a double-blind study and whatnot. How does the solenoid create a magnetic field? Well, we talked about the basics. The basics are you have current. Current makes a magnetic field. But now we have current going through this coil, and we have a way to calculate, using Ampere's law, what the magnetic field is created in the solenoid. So I'm going to do it on this picture right here. So here's my solenoid. If I'm going to use Ampere's law, well, first let's just rewrite Ampere's law so we remember it. The circulation on a closed loop, so I'm going to put here closed loop, is equal to mu watt times the current enclosed. So in my picture here, I need to choose a shape that's going to be easy to calculate that circulation. So we had a simple symmetry when we were doing a wire. Now it's not so simple. I'm not going to ask you what shape I should choose. I'm going to show you the shape I'm going to choose and then explain why. So the shape I'm going to choose is that. And you might be like, why? Why? Reasonable answer. First, we have to make an assumption. Assume a long solenoid. Why make an assumption of a long solenoid? If it's a long solenoid, then this figure here, which is pretty exaggerated, is going to be very uniform in the center. That is, the magnetic field in the center is just going to be constant and horizontal. It doesn't matter if I put the bottom of my rectangle there, anywhere in here, it's going to have the same magnetic field strength, and it's going to be parallel to the side. So that means when I do the circulation, notice I have four sides here. So let's call this side A and this side B. So B is that distance and A is that distance. When I do the circulation, I'm going to have four pieces because I have four sides. So let's go and do that circulation. So if I do the circulation calculation, I'm going to have the magnetic field inside. Now, what's the angle between my wire and the magnetic field inside? I'll zoom in. What's the angle between my blue line and the red line? They're parallel, so that's an angle of 0. So how much is parallel? All of it by definition of they're parallel. So for that one, the amount parallel is just going to be that length of the bottom piece, which I identified as A. So that's the magnetic field, that's the part of the circulation that's inside of my solenoid. Now I have the next piece. Looking at this side of length B, going from the bottom to the top. If I have a big solenoid, Once again, I'm just going to have horizontal magnetic fields if I'm in the center based on symmetry. And so what's the angle between my side of length B and the external magnetic field? Or excuse me, and the magnetic field that's produced? They're perpendicular. So how much is parallel if they're perpendicular? 0. So I am just going to put plus 0 for each of the two vertical sides, because the magnetic field is perpendicular to the length. I only have one side left, the one up here at the top. And this one here is a little funny. What matter did it make how long B was? Didn't matter. So what I'm going to do is say, let me make B really, really long. And you're like, why? Why do you want to make B really, really long? Well, what can you tell me about the magnetic field if I get really, really far away from the solenoid? It's going to be 0. So I'm going to make B really large, because in that case, it's just going to be 0 magnetic field for the last one. So my shape made it so the circulation was just the magnetic field inside times that length A that I had for the width of my rectangular loop. So now that we've gone through and calculated the circulation, notice this is very different than the circulation for a single wire. Now that we've calculated that, we have to say that's equal to mu watt times the current enclosed. Well, if I look here, in my picture, I made it so only one wire goes through my box. Actually kind of random. The current enclosed is going to be equal to the current in one wire multiplied by the number of wires that are going through my box. So if I had 2 wires, it'd be 2 times the current. If I had 3 wires, it'd be 3 times the current. So to be general about this, I say that the current enclosed is equal to the current multiplied by my length A, and then multiplied by the total number of turns in my solenoid divided by the total length of the solenoid. So capital L is the total length of the solenoid, and capital N is the total number of loops in the solenoid. So I might have a solenoid, there's a group making a Tesla coil, and those people might have 10,000 loops in a length of 20 centimeters. And so that's what they would have. N would be 10,000 loops, and the length would be 20 centimeters. And then I have the little a for saying how much of that, how many loops are going through this small length A. So putting that into my equation, so now let's simplify. Simplify by dividing both sides by A. And what happens? A canceled out. It really had to, because A was meaningless. It was just I choose some width A. If A mattered, then it would be a problem. And so we have the magnetic field inside the solenoid is equal to mu watt I times the total number of turns divided by the total length, or sometimes we write mu watt I lowercase n, where lowercase n is defined as total turns over total length. So that's once again an application of Ampere's law to calculate how much magnetic field is created in what location. Okay, what location did we use it for here? What part of the solenoid? Inside the solenoid. So this equation is the magnetic field inside the solenoid. It wasn't a calculation of the magnetic field outside of the solenoid. The magnetic field outside the solenoid, just like for the magnetic field for a wire, is going to be much weaker. But in a class like this, we're not even going to worry about what the strength is of the magnetic field outside the solenoid, just what it was inside. So now given this equation, let's just look at this. What things can you do to make the magnetic field inside a solenoid stronger? Okay, you can make it have more turns N if it's in the same length L. Or you could make it have the same number of turns but a shorter length solenoid. How did the radius of the turns come into this? It's not there. So it doesn't matter if you have big loops or small loops, it matters how many loops you have per centimeter. The more loops per centimeter, the stronger the magnetic field is going to be created. Also, the bigger the current, the stronger the magnetic field is going to be created. And finally, going to the question that Ashley asked, if you use something that has a higher magnetic permeability, then you'll make a bigger magnetic field. And so a demonstration that I will do on Tuesday, tomorrow, we will use a coil and see what difference it makes if we put something that's iron in the coil, in the solenoid, rather than if we have air in the solenoid. Do you have a question, Ashley?
I was wanting you to repeat the two things that you said about what makes the field stronger. The more loops per centimeter, the stronger the field. And then what was the other thing you said?
Well, it would be three things in general. More loops per length, more current, right? If you increase the current, you're going to increase the magnetic field proportionally, and a higher magnetic permeability. So here is a very practical example. Now, I talked about my medical example on my shoulder. I have also had just about every other medical procedure you can imagine, including an MRI, right? Hurt my knee playing football just before I came here to Union. And so an MRI, magnetic resonance imaging. When I was a young sprout, that's not what they called it. Anybody know what they called it when I was a youngster? They called it nuclear magnetic resonance, NMR. And people said, oh, nuclear, it's dangerous, danger. It's not dangerous at all. They're simply probing the nuclei of the atoms in your body. Because you know what? Your body is made up of atoms. Those atoms have nuclei. No danger there. But because people were worried, they just dropped the N. Sometimes they'll put a lowercase n in front. And they put an I at the end, and they call it MRI, magnetic resonance imaging. In both cases, what they're looking at is the energy required to flip the spin of, the spin of the nuclei of atoms. And you're like, flip the spin of the nuclei of atoms, what does he mean? Well, what does the spin mean if you have an atom? Well, if you've learned electrons, what does the spin mean in electron? Here's what it doesn't mean. Doesn't mean that. It was named spin because if you have current going around a circle, it makes a magnetic field. And people noticed that electrons had a magnetic moment. Guys, an electron behaves like a little bar magnet. And so they said, it must be because the electron has charge and it's spinning. And so they called it spin. But now we understand that is not possible. The electron could be zero volume, probably not. But we can calculate its maximum volume, its maximum radius, and based on that maximum radius, it would be impossible for it to spin fast enough to create its magnetic moment. So it can't be actually spinning to give it its magnetic moment. But we've all gotten comfortable calling it a spin, so we still call it spin. So spin up, spin down, that means its magnetic moment is either aligned like this or like this. And as I think I've said before, quantum mechanics, being the weird thing it is, says that it can't be exactly aligned. We learned, I just reviewed it today, that if I put a magnet in a magnetic field, there's a torque to try to make them align. But quantum mechanics says that an electron or a proton, because protons have spin, or a neutron, because neutrons have spin, can't align with the magnetic field. It'll have a torque to try to make it align, but it won't align. And instead, what it does is it precesses. It goes like this, so its magnetic moment is going in a loop around the direction that it wants to be aligned. And if you have a stronger magnetic field, it goes at a higher frequency in that precession. And so what they're doing with the magnetic resonance imaging is actually probing for a really strong magnetic field, what is its precession rate? And from that, different nuclei have different precession rates that they will have, and you can differentiate what the nuclei are. So you can see where, for instance, hydrogen is. So for NMR or MRI, the higher your magnetic field, the more accurate you're going to be able to be. So they want really strong magnetic fields. So they put you in this machine that's a huge coil, a huge solenoid, to make a really strong magnetic field. So if you ever go in for an MRI, one of the things they tell you is you can't have anything that's metal. Why not? Because it will be torn away from you. Right? Nobody wants that. So no metal. This here is a special kind of coil called a Helmholtz coil. Oops, second H is not capitalized. The Helmholtz coil is designed so that you have two separate coils separated by a distance equal to the radii of the coils. What's the point of the Helmholtz coil? It gives you a very uniform magnetic field in the center, just like you would with a continuous coil, but you have that gap. So it's a simpler way of making the strong magnetic field that allows you to, reach in, have stuff going in there. So our next question, and it says, do you see? Some people just say, I don't see. Doesn't mean it's not there or is there. Do you see an exploitable symmetry to apply Ampere's law to an infinite solenoid? An infinite solenoid means one that extends forever horizontally in my picture here. No, it's open. We have 11 people who've answered. Okay, 12601. Jeffrey, explain this one.
Looking at the field lines, if the solenoid continued on forever, the field lines would all be, just parallel and straight. So, but you got to realize that the field lines are all in a circle around the center, so therefore,
So which,
A.
You said A, the cylindrical? Okay, so he said cylindrical. This is the example that I did. The actual exploitable symmetry is something else, because you do have a cylindrical symmetry there, but it's not exploitable, because what you would have if you made a loop that did a circle around it is your loop is going this way and the magnetic field is going this way. What's B dot L? If B is perpendicular to L, then B dot L is 0. And so you'd have a circulation is 0, and then you have, well, how much magnetic field is enclosed? Well, if you're going around the solenoid like this, you're actually not enclosing anything because the current, you don't have anything cutting through that. And so you'd have 0 equals 0 for your equation. It's true, but it's not helpful. And so that's where we had this shape here. Now, a final thing on this, and then I'll answer you, I might answer before. A final thing on this is I said, let's stretch this out to be infinitely long. And any reasonable person would say, wait, that doesn't make sense, right? Well, here's the thing. You have the magnetic fields are not going to be perfectly perpendicular on the sides. And so what's going to happen is you're actually going to have, if you're at the symmetrical center, no matter how far out you go, you're going to have the amount that's added by the not perpendicular parts is going to counter what you have at the end. And so it turns out that you just make the approximation of a very, very narrow, very tall wedge and stay with the perpendicular on the sides and go to infinity, and you get the same answers you would with the much more difficult to analyze problem. Okay, what was your question?
So what was planar? That was
A planar symmetry, a planar symmetry would be that it's all in a plane, but since this is going like this, it's not really planar symmetry.
not.
The real key here, the planar was just so I could have another answer. The key was, even though it's a cylindrically symmetric object, that's not symmetry we can exploit. All right, and we only have 1 minute. I will wave my hands at this problem. Question?
Sorry. Is the right hand rule different for a solenoid?
No, for a solenoid, it'd be just the same as for the current in a circle. Okay, this question here, I think it's in the SHW, but not the homework. Find the force on the, actually, I haven't made the homework yet. Find the force on the loop. So I have this loop down here. How do I find the force? I start by saying I have current I1 that's going to make a magnetic field. What direction is that magnetic field going to be below? Using the right-hand rule, it's going to be going in. So I'm going to have a magnetic field here that's like this. Now the magnetic field is weaker as you get farther away. I calculate what the magnetic field is and what the directions of the forces are on each side. Based on symmetry, the left and the right sides will have the same magnitude force, but one is IL cross B. So the L on the right side is down and the B is in. So on your left side, the force is coming toward the center. On the right side, it's also going to be coming toward the center, so those two are going to add up to 0. I don't have to do calculus to calculate what the strength of those two forces are because they add up to 0. And then for the top and bottom, I just use force equal IL cross B, and these have finite lengths, so it's easy to calculate the total force. Keep in mind the magnetic field is going to be different on the top and the bottom, giving me a net force that's not 0.